Okay, let's talk about 25 on 7.2. So another kind of interesting one, and I think there are a couple ways that you could approach this one, maybe. Let's try it out. So what I'll say is that, if you were thinking, well, I'll differentiate this because it goes down to 0, and then I'll integrate this, well, I mean, normally, yes, you would want to integrate the polynomial thing, but in this case, we don't really have a technique for integrating e to the x squared. So you're going to have to choose the other way around, right? So one way that you could do it would be like this. You could say, I'm going to integrate x cubed and differentiate e to the x squared. Because I don't know how to integrate e to the x squared otherwise, right? If you do that, then the derivative of e to the x squared is going to be e to the x squared times the derivative of x squared, which is 2x. So you're going to get 2x e to the x squared. And then if you integrate x cubed, you get x to the 4th over 4. Now, notice that when you multiply these things together, the x's will cancel, and you'll be left with an x cubed e to the x squared, which is just what you started with, right? So in a way, this is very similar to number 21, right? Because I would stop at that point and I would say, okay, so this is going to be 1/4 x to the 4th e to the x squared minus, right, minus 1/2 times the integral of this x. Oh, actually, they won't cancel, will they? It'll give you an x to the 5th. It'll be an x to the 5th e to the x squared dx. Shoot, I was thinking that they would cancel and give you an x cubed, and then see you'd have what you started with, and you could solve algebraically for the integral. But no, it doesn't work out that way, does it? Ooh, this gets you. This is worse. It gets you further away. So let's abandon ship. All right, let's not try it that way. Okay. Well, what else could we do? What else could we do? We could try a u sub, right? So we could try a u substitution, and I think the obvious choice for the u substitution would be let u be x squared. Then du is going to be x dx. We have an x cubed dx, but notice that if you take one of the x's from here to give you du, right? So if you call this x times x squared, well, remember x squared was u, and the other x gets absorbed into the du part, right? So I think that's actually going to work out for us, right? If we let u be x squared, then du is going to be 2x dx. Okay, I can rewrite this integral as 1/2 times the integral of 2x times x squared. Right, the 2 cancels the 1/2. The x times the x squared gives you x cubed, and then e to the x squared dx. So now the 2x dx will become a du, and these x squareds will just become u. So this is going to be now 1/2 times the integral of u e to the u du. Now that thing you can integrate by parts. For sure, right? Super easily, right? So we can differentiate the u and integrate the e to the u. This is going to go to 1 and then 0. This is going to just stay e to the u, e to the u. Okay? And we'll do plus, minus, and then plus, but there's not going to be anything left to integrate because 0 times e to the u is just 0. So we're going to get 1/2 times u e to the u minus e to the u, and then plus c. Okay, the only thing left to do is to back substitute now. U was really x squared, so this is 1/2 times x squared e to the x squared minus e to the x squared plus c. And there's that one. So I guess, yeah, I mean, if you try to jump straight to to integrating by parts, I don't think that's going to work out nicely for you. Maybe if you had kept going with the tabular method, something nice would have happened later on. I don't really know. But I think starting off with a U sub first really simplifies things quite a bit, right? So that's that one.